Hello, my name is Karl, and today I'm gonna present a summary of what I learned throughout the entire course. And for each unit, I will present one or two interesting results or theorem that I've learned. And for some of it, I'll present a simple proof or a rough draft of the proof. And the others that are too complicated, I will only mention the results. Okay. First of all, I will start out with some stuff I learned in group theory. So given a group G, we may consider its subgroups, in which we will know as H. And the most important question that we were trying to solve was that when is the quotient set, which is the set of equivalent classes defined by H, given by A is equivalent to B if so for all equivalent classes, and then let's also denote this as the equivalent classes including the element A. And then we want to know when is this set once this set a group with the multiplications defined by this. So when is this well defined in this set to make this a group? And then it turns out that when H is normal, G over H, the quotient group is G over H is a group with the multiplications defined this way. And H is normal if and only if which is defined to be the set if and only if this thing is equal to H, or equivalently the left translation of H is the same as the right translation of H. And then furthermore, this thing is also enough for showing that H is a normal group. And then we next talked about the group homomorphisms on G. So there is some relations between the group homomorphisms on G and the normal groups of G. So for each homomorphisms on the group G, we can consider its kernel. Which is all the elements that's getting mapped to one by the homomorphism Y. And then in this case, for each homomorphism on the group G, its kernel is actually also a normal group of G. And to show this, pick an arbitrary elements that's in G. Then since H is in a kernel, we know that Y of H is equal to 1. So then this thing is equal to to this, which is again equal to 1. And then next, I want to talk about a very interesting group that's kind of important to abstract harmonic analysis, which is the special unitary group on the on C2. And then the elements in SU2, after some computations, is always in the form where its determinant is equal to 1. So it's also equivalent to this. And in particular, since A and B are complex, this actually also implies that suppose A is equal to and B is equal to, then this thing actually also implies so each element in the special unitary group is also a solution to this equation, and they're kind of isomorphic to each other. So we also know that the special unitary group is isomorphic to the sphere in R3. I mean R4, sorry. Oh yeah, yes. Oh yeah, right. Hold on. Yeah, sorry. Yeah. And then next we discuss about the actually for a group G, actually we can assume it to be a topological. Actually, let's just assume it to be a regular group for now, like just arbitrary groups. For any group G and H, we may consider the set of homomorphisms from G to H, and we are wondering when is this set a group? And after some computations and checkings, we notice that the homomorphism, this set is a group if and only if H is abelian. And why is that? It's because if H is not abelian, then the inverse of a homomorphisms in this set might not always exist. And to see this, pick an arbitrary elements A, B. That's in G. Then the identity of this set, when this is a group, always have to be the map F that maps everything to the identity of H.
When you say it's a group, well, then just dealing with, are you going to say what the multiplication is? Are you going to say what the group operation is?
Yeah. So the group operations in this case is defined by the point-wise multiplications. So so suppose we have them by 1 times by 2, then this is defined to be let's also put element G here. this is the group operations defined on this set. And when is this when does this group this operations make this a group is when H is a billion. And to see this, consider AB that's in G, and after some checkings, if this is a group, then its identity has to be the map that sends everything to the identity of H. So in this case, for any elements A, B that's in G and an arbitrary homomorphisms that's from G to H, then when we multiply by its inverse, this thing has to be equal to f. I mean not f, but f of A times B, which is equal to 1 by definition, because f.
Sorry, are you talking about homomorphism or, I mean, in homomorphism doesn't always have a class.
Oh, so what I'm doing is
What do you mean by hom or G of H?
Oh, so
Homomorphism, or do you want vectors that are also bijective?
it's the set of homomorphisms that's from G to H. Does that answer your question, or?
Then how do you know that there is that phi has an inverse?
Oh, sorry. These are elements of this set. Like,
yes, but phi, okay, if not all the homomorphism have an inverse, so how do you know that phi minus 1 exists?
Oh yeah. So we're trying to show that, like, if this thing exists, then it has to satisfy certain properties. Yeah. So sorry about that. So if this thing exists, then the result has to be equal to 1, which is, sorry, like I mean like the identity of H. And then
Where do you get the equation F A B from?
So this is technically equal to y times y inverse of A times B, right? And this two multiplied by each other should be equal to the identity, which is and then so here what happens is that if we multiply the inverse of these elements on both sides, then we obtain like this element's inverse that's in H. Okay, and then and the inverse of this elements, by looking at this, we know it has to be equal to right. And then if the y inverse in this case is also a homomorphism, then this has to satisfy. Then this thing also has to be equal to this, which shows that AB has to be equal to BA.
See where you, oh, that equal sign is coming from the very left-hand side.
Mm-hmm.
So, well, no, why is you, why have you always, why have you run, suddenly got, phi inverse?
Oh,
Very good. What's the last component?
So sorry, I think I shouldn't use equality here, but if like y inverse in this case is a homomorphism, then it has to also satisfy this equality.
No, you're not using that because the fact that you have an homomorphism will give you phi of b minus 1, not phi minus 1. If you have an homomorphism, that will bring the minus 1 inside, not around phi. What you are using, I think you are using that property that again. You are using that phi minus 1 AB is equal to phi AB minus 1.
So from here? Oh, sorry.
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 Sorry, I don't know how to speak from that.
Yeah.
The fact that it's an homomorphism would give you this one,
Uh-huh.
not this one.
Oh.
What you are using is this property here
Mhm.
that tell you that if you have the minus 1, you can bring around phi. But for example, if you take B equal the identity of G, you get from this, you get that phi minus A is the same that phi of A minus 1, no? This one, and this is what you are using. You are rewriting this as phi minus 1 of B, phi minus 1 of A, and now use an homomorphism.
Oh.
That is this. So
Okay.
you need the one extra step.
Oh,
You
okay,
are
okay.
using this to get this equality, which is this one here, but with taking one of the two, we put that in.
Uh-huh. Okay, okay. Thank you so much. Thank you so much.
I think that is what you are missing.
Um. Okay.
If I have a inverse, then it must be pointwise inverse.
Uh-huh.
I think I'll use that.
Yeah, if it's pointwise multiplication, then the inverse has got to be the pointwise inverse. But you're somehow showing that that's not possible in general. But why is it not possible in general?
So my argument is that if A times B is not equal to B times A, then this thing might not be a homomorphism.
Well, assuming that to define the group operation, you don't have to worry about it and whether it's or not. It's just a fact from G to H and the pointwise multiplications. It's a big group. And now you are looking at a subset, which comes from homomorphism, and you want to show that that is a subgroup. Maybe you want to show that it's closed and I mean you take two homomorphism and take pointwise multiplication. It should come from something.
So when you're showing it's not closed under interest.
I'm sorry, I didn't quite hear that.
Well, the goal is to show that set, right, of homomorphisms is not closed under pointwise interest. Right? Or to show, well, I guess it doesn't exactly do that, but
Certainly, if you look at all maps from any set into a group, then with pointwise multiplication, that's a group. So what goes wrong? That's what goes wrong. So the and if you have a subset, if it's a subgroup. Well, if there's a subset with the usual multiplication, the same multiplication, then the inverse is going to have to be the same as it is in the big set. So we know what the inverse has to be if it exists. And you're just saying that in general, the inverse is not homomorphism. Inverse, the inverse of the function just from G into H. Pointwise inverse is not the whole homomorphism. But why is that? you said at the very end, okay, so if the phi inverse AB is equal to phi inverse BA, well, that's what's required, right? But what's wrong with that?
There could be nothing wrong with that. And I think this proposition, this statement could be, I mean, even H is not abelian, the homomorphism from G to H still can be a group. Because this can be just a trivial set, maybe single number.
Yeah, so it's
It's not acceptable.
so it's not quite clear. It's not quite clear what your main statement is. Your main statement is just that if H is abelian, then you get a group, and that's fine. That's the main thing you stated. That's the only thing you stated. If H is abelian, then the homomorphisms form the group, or some, as a subset of the set of maps, the group of the
Yeah.
point was.
Oh, I was trying to show that when H is not abelian, then the inverse does not
If
exist.
it's not true.
Oh, I see. I think there might be something wrong with my.
Sorry?
There might be something wrong with my text.
These
It's
steps
not.
are right? And it shows that C of AB has to equal C of BA. But there could be homomorphisms that do that, right? Even if H is not a billion. And it could be that there's all homomorphisms. So for the homomorphism, right, so proving that C of AB has to equal C of BA does not apply that H is billion, because we don't know that all the elements of H are hit as the image of the homomorphism.
Oh, okay. I see. Okay.
And it might even be true that every if an arbitrary homomorphism, the inverse, more pointwise inverse is a homomorphism for some G and H, where H is not a B.
Yeah, so this was what John Long was saying before, right? For example, right, it could be that that the only homomorphism from G to H is a trivial. Right? So depending on what G and H are, like for instance, G and H are finite groups, and the cardinality of the groups are relatively broad. You cannot have any homomorphism. And so then in that case, it would be true that the homomorphism for the group because it's trivial.
At least they have to be trivial on the commutator subgroup.
Yeah, exactly, right. So more generally, it could be that you have some situation where the commutator subgroup of C, all the homomorphisms are trivial, right? And being trivial on the commutator subgroup means exactly what C of A is.
Okay, I understand.
So that could happen.
Okay.
Okay, well, this is a good example, a good question. So, what's next?
Okay. And next we go into topological groups. And one of the most interesting and useful results that I've showed is that for G and H, where now they're topological groups. Oh, sorry. We only have to look at a single topological group now. Then the map that sends elements in G to where and this is from G to G. This map is a homeomorphism. And to show this, we can define like the decomposed f of a into the map and then we just show that this map is continuous and this is continuous by assumption, since G is a topological group. So their composition is again continuous. And from here, we can use this property to prove a lot of things. For example, if G and H are a topological group. Oh, sorry, hold on. Actually, never mind. No. And phi is a homomorphism from group G to H. Then to show that it's continuous, we only have to show that this thing is continuous at one point. And then I will sketch the proof. So basically, F being a homeomorphism implies that F is a open mappings. So since F is an open mappings, we know that for any open sets that's in G, any translation of that open set is again open. And then so for every, so to show that phi is continuous everywhere, we just pick an arbitrary point and show that it's continuous. And since phi is continuous at one point, I can assume that it's for now, let's suppose that single point is the point 1. So phi is continuous at 1. And then I will show that that will imply that phi is actually continuous at every point. So phi is continuous at 1 implies that for any open set thing in H that is open, there exists a open sets in G that covers the point 1, such that the image of U is contained in V. And then the proof of this is that we first pick a point, arbitrary point in G, and take a open set VG, in H that covers the elements phi G, then we may shift it, we may translate it so that this open set covers the elements 1. So we can shift it by this element, and this open set now covers the elements in which case we know that this is the identity of H. And then by our assumption, there's an open set that's in G that covers the element 1. But then if we translate it by phi G, then this open set covers the elements. And then when we wait, sorry. I shouldn't write this. I should just write G. Sorry. Then when we take the image of this set, then this set is an open set that's included in like VG in this case. Yeah, covers. Oh, sorry. This set covers G. Sorry. And then in particular, this homeomorphism does not only gives us this result, it also gives us that for any set V, whenever V is compact, a translation of an element in G will again gives us a compact set, since this is a continuous function, as well as a closed set. Then any translation of that closed set is again closed. And so I think this is a very useful thing at proving if a topological group is locally compact, because then we only have to find a single point that's covered by a compact set. Then we can translate that compact set so that it covers like any points we want in the group.
Didn't quite catch that statement. Is it not true for any topological group that for continuity it's enough to have it as a single point?
Because we know that any translation of the compact group.
Are you just stating this for locally compact groups?
No, this is what's easier, right? You finish the first year, and then he's talking about a different.
Well, what is the what's the original? What's this over here?
Oh, this shows that phi is continuous at arbitrary G that we picked.
That shows that if P is continuous at the identity, then it's continuous at the quantity.
Okay, but that's just because, I mean, if you have any topological space, and you have then a map into some other topological space, continuity means continuity at every point. Okay, but if any 2 points are connected by a homeomorphism, obviously that's true. I mean, it's enough to look at 1 point. That's a trivial statement. And for any topological group, you have translations or homeomorphisms. Take the 1 point and point. But what's the new statement?
So we know that this map is a homeomorphism. So this map right here.
Left translation.
Yeah. So this map is a homeomorphism. So this is also a continuous map. So it maps compact set to compact sets.
Well, what's the question?
Okay, so basically I'm claiming that I think this might be trivial now, but since this maps compact sets to compact sets,
Yeah, but you're proving something. What's the actual?
I'm not proving something. I'm stating
We're pointing out that you can prove local compactness in a simpler way using this fact.
oh yeah.
Proving local compact.
Yes, you want to check that your group is locally compact. Importance for the theory.
Well, okay, so it's like, we're moving from a single point. It's like moving continuity from a single point. Compact neighborhood from a single point.
Yeah, so
Sure. You have polymorphisms that take an arbitrary point to arbitrary point. Then compact sets will go to compact sets, and compact neighborhood will go to compact neighborhood.
yeah.
And then every okay, well, you have to check if that's true, that open neighborhoods go to open neighborhoods, and so if every open neighborhood contains a compact neighborhood, then that would be true for all points. It's true for the single point. So I agree. You have to check go through. You have to go through the steps. Yeah.
Is it point to stop?
Oh, okay.
All right, let's